Hi and welcome to the GCSE Cadlam Cymru sessions. This is the autumn session and this is number 4 in the chemistry section. This one will focus on calculations in Year 10 chemistry. So far this term we've had 3 sessions already. The first was on atomic structure and the periodic table. The second on elements, compounds, formulas and balancing equations. The third was on Group 1-7 and Group 0 chemistry. And this final session in this particular collection is on calculations in Year 10 chemistry. Now, obviously, these calculations will be useful in Year 11 as well, but they're first introduced to you whilst in Year 10. So this is just a list of some of the calculations we will be covering in the session today. Number of atoms in a formula, the relative atomic mass, relative molecular mass, percentage mass, moles, percentage yield, reacting masses, empirical formula, and RF values. Okay. Now, some of this to begin with was covered in the second session. So if you have been following us, then you will have done some of this before. But it's always good to have a little recap and go back and see if you can remember what we did. So the first thing we're going to look at is the number of atoms in a formula. Okay, so it's quite a common question, in particular at the beginning of a paper. So the number of atoms in a formula. Can you tell me what the number of atoms we have there is, please? Okay. Now remember, with any of these, and I'll try not to repeat myself too much throughout the session, but you can pause and you can attempt the question and then you can restart so that you can see the answer once you've attempted it. So let's have a look. So here is the breakdown. So we have 2 nitrogen atoms, 8 hydrogen atoms, 1 sulfur, and 4 oxygen. Now, just be careful here. Whenever you have brackets, you may remember from the previous session that you have to multiply by whatever is inside the brackets, okay? So hence the 2 nitrogen and 8 hydrogen atoms. And then you add them all together, and the total number of atoms in ammonium sulfate is 15. Okay, so pretty straightforward. Let's have a look at the next. So can you please tell me the number of atoms in the following formulae? So we've got calcium carbonate, sodium sulfate, and aluminium hydroxide there. Can you calculate those? So pause this and attempt the question. Okay, so let's have a look then. So we have 1 calcium, 1 carbon, and 3 oxygen in calcium carbonate, which gives you a total of 5. Okay, so 5 atoms. In sodium sulfate, we have 2 sodium atoms, 1 sulfur atom, and 4 oxygen atoms, which gives you a total of 7 atoms. And then in aluminium hydroxide, we have 1 aluminium atom, 3 oxygen atoms, 3 hydrogen atoms, giving you a total of 7 atoms. So hopefully that's nice and straightforward. Just be careful with any brackets. Make sure you are remembering to multiply by what's inside the brackets. Okay, so again, something we touched on in the second session of this series is relative atomic mass, AR. This is the mass of an atom relative to the mass of the carbon atom, carbon 12. The mass of this carbon is given as 12, and the masses of other atoms are then calculated from that. These figures are called relative atomic mass. So here we have sodium, okay, taken straight from the periodic table. Can you tell me what is the relative atomic mass of sodium? Well, hopefully, we've got 2 numbers to choose from there. Hopefully you remember from the previous session and from work you've done in school that the biggest number, 23 there, is the relative atomic mass. that is the number of protons and neutrons within an atom. And the smallest number, of course, is just the number of protons. Okay, that's the atomic number. So hopefully you have a periodic table somewhere nearby, whether it's up on your wall in your classroom or in your book. Okay, so get that ready now. You will be using it at points throughout the session. Okay, so it's quite handy, it's quite useful to have that on you. The first one, could you please have a look at the relative atomic mass of the following elements? Okay, so have a go at that. So we have calcium, strontium, bismuth, and xenon. Okay, so using the periodic table, hopefully we have the following numbers. So 40 for calcium, 88 for strontium, 209 for bismuth, and 131 for xenon. Those are just taken straight from the periodic table. Remember, you will have a periodic table with you in the exam, so you do not need to memorize any of these, okay? But you do need to know where to find the information, okay? And lots of mistakes are made between confusing relative atomic mass with atomic number. So make sure you know which is which. Okay, so isotopes next. Isotopes, okay, this is a really important definition for you to learn. They are different atomic forms of the same element, which have the same number of protons, and of course electrons, but a different number of neutrons. So there's a really important definition for you. Make sure you know that off by heart, okay? We've got some examples here for you. These are isotopes of chlorine, and as you can see, there are two isotopes. Notice the relative atomic mass for these are different. So you can see the pink there. We've got one which is 35 and one which is 37. So the relative atomic mass uses the average mass of the isotopes of an element. And as we can see here, there are two isotopes of chlorine. So the relative atomic mass will be looking at those two masses and getting an average, okay? So in order to do that, okay, we have to consider its relative abundance. And as you can see underneath the symbols for both, the relative abundance of these two isotopes is 3 to 1, okay? So there's 3 times more chlorine 35 than there is of chlorine 37. So we need to take this into consideration when we calculate the relative atomic mass, and there's a calculation there for you on the bottom right. So what we would do, we would multiply the relative atomic mass of the isotope by the abundance, add that to the relative atomic mass of the other isotope, multiplied by the abundance, over the total, which gives you 35.5, okay? So that is the relative atomic mass for chlorine, and that is the number that you would find in the periodic table. So notice that in particular when you move on in chemistry, so in particular to A level, for example, you will notice that the relative atomic mass for elements, they don't tend to be whole numbers because of the presence of isotopes, okay? Next, we have relative molecular mass or formula mass, okay, which is known as MR. The relative formula mass is the total mass of a compound. And to calculate this, we add all the individual ARs of the atoms that make up the compound. Okay, so ARs when you're looking at one element. The MR is when you're looking at a collection of those, a compound. Okay, so first task, calculate the relative molecular mass, the MR, for Fe2O3 iron oxide. Okay, so once again, using your periodic table, let's have a look. So here's the breakdown for you. Okay, so the first thing you would do would be to use your periodic table and you'd find the AR for both iron and oxygen. They are on the left-hand side on this screen here. So we've got the AR of iron is 56 and the AR of oxygen is 16. Now, you also need to consider how many iron atoms and oxygen atoms there are in this compound. So as there are 2 iron atoms, you must multiply 56 by 2. And as there are 3 oxygen atoms, you must multiply 3 by 16. On the right-hand side, you can see you've got both of those totals there. So you've got 112 and 48. And therefore, to calculate the MR, you just have to add those two together. So nice and simple, gives you 160 as a total. And that 160 is the relative molecular mass for iron oxide. Okay, right, well, it's your turn to try an example as well. So can you calculate the relative molecular mass for aluminium hydroxide, please? Pause this if you'd like some time to do the workings out. Okay, let's have a look. So broken down for you here, we have the AR of aluminium is 27, and there's only one of those atoms. So 1 times 27 is 27. The AR of oxygen is 16. And because we're multiplying by the number outside the brackets, there are 3 oxygen atoms. 3 times 16 is 48. And then if we look at hydrogen, the AR of hydrogen is 1. However, there are 3 of them. So it gives you a total of 3 times 1. And then all you need to do is add all of those together to give you the relative molecular mass, which is 78. Okay, so the next calculation is going to be percentage composition of compounds. After calculating the MR, it is possible to work out the percentage of an element in a compound using the formula. Okay, this is the formula here. Percentage mass is the AR times the number of atoms of that element divided by the MR of the whole compound, and then multiply that by 100 to give you a percentage. So really straightforward. Let's have a look at an example. So here we have the following question. Calculate the percentage mass of magnesium in magnesium carbonate. Okay, and the formula is there for you, so MgCO3. I've also popped down there the ARs from the periodic table, just in case you don't have one at hand. The AR of magnesium is 24, AR of carbon is 12, and the AR of oxygen is 16. You will use lots of these elements over and over, so you will get to know some of these off by heart, okay, such as carbon and oxygen, for example. So first thing you need to do is calculate the MR of magnesium carbonate, okay, that's the whole compound. So 24 times 1, because there's only 1 magnesium in that compound, plus 12 times 1, because there's only 1 carbon in the compound, plus 3 times 16, because there are 3 oxygen atoms. And that gives you a total of 84. Okay, so that's the MR for magnesium carbonate. But you're being asked to calculate the percentage mass of magnesium in magnesium carbonate. So out of that 84 total, 24 is magnesium. So in order to calculate the percentage, you must divide 24 over 84 times the 100, and that gives you a percentage of 28.6. Okay, so that is the percentage of magnesium in magnesium carbonate. Okay, so let's try this next one then. Calculate the percentage mass of carbon in carbon dioxide. Okay, so have a little go at that. Do you remember the ARs for carbon and oxygen by now? Do you know those off by heart? Okay, let's have a look then. So the AR of carbon is 12 and the AR of oxygen is 16. Well done if you got those. The MR is the first thing then you need to calculate. So that's a nice and simple one. 12 times 1 because there's 1 carbon. 2 times 16 because there are 2 oxygens. And that gives you a total of 44. So out of that total of 44, how much of that is carbon? Well, 12 out of 44 is carbon, multiplied by 100, and that gives you 27.3%. Now, if you were to be asked then, well, what about the percentage of oxygen in the molecule? You wouldn't need to do all of that calculation again because, as you know, percentage is out of a total of 100. So 100 take away 27.3, which is how much carbon there is, will leave you with 72.7%, which must be how much oxygen there is. Next, we're moving on to moles. So the mole is a term that describes a specific number. So for example, we know that a dozen is 12, a baker's dozen is 13, a score is 20, a hat trick is 3, a pair is 2, a century is 100, and so on and so on. I wonder if you can think of any more examples. Okay. The mole, however, is a much larger number than any of these, and it is, as we can see below. Now that is 6 followed by 23 zeros. Okay. Or, because that's quite hard to write out each time, we could write it as 6.02 times 10 to the 23. And that's how many atoms there are in a mole. This number is also known as Avogadro's number or the Avogadro constant. So you may see it written as this too. So let's have a look at some examples of calculations involving moles. First of all, have a look at this definition. A mole is defined as the number of atoms in exactly 12 grams of carbon-12. 12 is the mass number of carbon, so 1 mole of carbon atoms has a mass of 12 grams. Now that might seem confusing, but we will be looking at some examples that will make it much clearer. Okay, so the AR or MR of a substance in grams is known as 1 mole of that substance. Okay, so that is a little bit clearer. Let's have a look at an example of what we mean. So if I was to ask you, what is the mass of 1 mole of iron? Well, you would look at the AR of iron, which is 56, and therefore you can say 1 mole of iron has a mass of 56 grams. Okay, so that's what that means. What about the following? Can you attempt these? So once more, you'll need the periodic table to have a look at the AR, the relative atomic mass, for both of these. But the first question is, what is the mass of 1 mole of nitrogen gas? And question 2, what is the mass of 1 mole of calcium chloride? So have a look at the periodic table. We need to calculate an AR or an MR here. Okay, so have a look and we will show you the answer now. Okay, so here we go. Nitrogen gas N2 has an MR of 28. Now that's actually quite tricky, isn't it? Because what we must remember is nitrogen gas exists, it's a diatomic molecule, so it would be N2 as opposed to N by itself. So please remember that. The MR, in fact, would be 2 times 14 because there are 2 nitrogen atoms present. So we can say that 1 mole of nitrogen gas has a mass of 28 grams. Okay. And then secondly, what is the mass of 1 mole of calcium chloride? Well, first of all, you calculate the MR of calcium chloride, which is 100. Okay. And then 1 mole of calcium chloride has a mass of 100 grams, therefore. Okay. So hopefully you can see, although the definition perhaps is a little bit confusing, when you have a look at some examples, it should make more sense. Okay. So let's have a look at a calculation involving number of moles. So to calculate the number of moles, we use the following equation. Number of moles is mass in grams of an element or compound divided by the MR of element or compound. Okay, so the first question here, just a little example for you to have a look at. How many moles of atoms are there in 4.8 grams of carbon? So what information are we being given there? Well, we're asked to calculate the number of moles. We know there are there's 4.8 grams of carbon. Okay, so that's your mass in grams. And we also know the MR or AR of carbon, which is 12. So 4.8 divided by 12 gives you 0.4 moles. Okay. Remember, if there's anything that you need some more clarity on, or you want to go back through and have a look at the definition again, pause this video, go back, watch it again. The beauty of this is you can do that. You can spend as little or as much time as you want on these sessions. Okay, so a few questions for you to work through now. Okay, I showed you an example of question number 1. Now we have 2, 3, 4, and 5 to have a look at. So question 2, how many moles are there in 640 grams of oxygen? And I've put O2 in brackets there just to remind you that this is diatomic molecule. Number 3, what is the mass of 0.6 moles of chlorine molecules? Okay, once again, a diatomic molecule there. Question 4, what is the mass of 0.1 moles of calcium carbonate? And question 5, 0.5 moles of a compound weighs 80 grams. Calculate its MR. Okay, so have a look at those. Pause this video clip and attempt the questions. Okay, so here we have the answers then. So how many moles are there in 640 grams of oxygen? So that's 640, okay, which is the mass in grams, divided by 32, because there are 2 oxygen atoms, both have an AR of 16 each, and that gives you 20 moles as an answer. Question 3, what is the mass of 0.6 moles of chlorine molecules? Okay, so by rearranging the equation, okay, we have 0.6, that's the number of moles, multiplied by the MR, okay, which is 2 of the Cl elements, and that gives you a mass of 42.6 grams. Question 4, what is the mass of 0.1 moles of calcium carbonate? So once again, we've rearranged the equation above, and we've got 0.1 moles times the MR, which for calcium carbonate is 100. So that gives you a mass of 10 grams. And finally, 0.5 moles of a compound weighs 80 grams. Calculate its MR. So we have the number of moles and we have the mass, but we don't have the MR. So we would do 80, which is the mass, divided by the number of moles, 0.5, gives you an MR of 160. Okay, so just make sure you are confident rearranging that equation. Remember to, you can draw it as a triangle, okay, with the mass at the top. And remember, you can just cover whatever you're trying to calculate with your finger, and there you have your calculation ready for you. So in an exam, in a test, draw out that triangle, make sure you don't make any mistakes whilst rearranging the equation. Okay, well done. Next, we're going to move on to percentage yield. Okay, percentage yield of a chemical. The amount of product we get from a chemical reaction is called the yield. The more reactants we put in, the higher the actual yield will be. The percentage yield tells us the overall success of the experiment. It compares the predicted yield with the actual yield. Okay, so here we have your equation. Percentage yield is actual yield in grams divided by predicted yield in grams times 100. Now, I know we've got in grams in brackets there. This doesn't have to be in grams. It could be in tons, okay? It could be in another unit, but just make sure those units are the same. And also multiply by 100, of course, because this is a percentage yield calculation. So try this question. In a manufacturing process, 12 tons of product are predicted, but only 10 tons are obtained. What is the percentage yield? Okay, so have a look at the equation. The actual yield over predicted yields times 100. Let's have a look at the answer. So nice and simple, 10 is obtained. So 10 divided by 12, which is predicted, times 100 gives you a percentage yield of 83.33%, which is actually quite a high percentage yield. I would be very happy if I was to obtain this in the lab. Right, let's have a look at reacting masses next. By using relative atomic masses, ARs, and relative molecular masses, MRs, it is possible to calculate how much of a product is produced or how much reactants are needed. And here we have an example question for you. What mass of magnesium oxide is produced when 60 grams of magnesium is burned in air? Okay, now I've written this out for you in a step-by-step way, just to make it a little bit clearer, a little bit easier to follow. And also when you come to answer a question such as this one, if you have some structure to your answer, then you are less likely to make mistakes. So the first thing I've done is I have looked at the question. Okay, we're burning magnesium in air to produce magnesium oxide. So I have turned that into a symbol equation, and then I've balanced that equation. Okay, so we have 2mg plus O2 gives you 2mgO. Okay, and that is a balanced equation. And that equation obviously matches what's in the question. So that's really important, because the next thing you're going to do is you're going to calculate the MR for both magnesium and magnesium oxide. Okay, those are the two key elements of this question. The fact that it's burnt in air, in oxygen, doesn't matter. Okay, we're not going to be looking at oxygen in this calculation. We're just looking at the two that are important in the question. Okay, and that would be the case every time you do one of these. So the MR for magnesium, first of all, we have 2 times 24, okay, which gives you 48. And then magnesium oxide is 2 times 24 and 2 times 16. Add those together, that gives you 80. Now then, as I'm looking at this, I see now that 48 grams of magnesium will give me 80 grams of magnesium oxide. Okay, so what I've done, I've got a ratio there. Okay, however, remember it's 60 grams of magnesium that I want to start with, not 48 grams. So what I'm going to do next is I'm going to have a look at what 1 gram would be, and that will be much easier then to multiply up to give me 60 grams of magnesium. So if we look at where it says C, therefore 48 grams would produce 80 grams. Okay, so 48 grams of magnesium will produce 80 grams of magnesium oxide. That is what you've just calculated. That was the purpose of the MR. Now, as I said, we're going to get that 48 grams down to 1 gram, because 1 gram is far easier to work with than 48. So for every 1 gram of magnesium, I know that 80 divided by 48, okay, so product divided by reactant, give me 1.67 grams of magnesium oxide. So 1 gram of magnesium will give me 1.67 grams of magnesium oxide. Okay, that is the point where you could go wrong. So just remember, in this instance, product divided by reactant, because you are trying to calculate the mass of the product. Okay, so that's why you divide product over reactant in this instance. Right, so if 1 gram produces 1.67 grams of magnesium oxide, then multiplying that by 60 will give me how much if 60 grams of magnesium is used, and the answer is 100.2 grams. Okay, so 60 grams will produce 60 times 1.67, giving me 100.2 grams. So you may need a little more time to have a look at that and the step-by-step, okay? But a few things to remember from this is make sure you write it out clearly. Make sure that once you've done your balance symbol equation, that you calculate the MR, but that MR will give you a ratio that isn't very useful. So you need to get that to 1 gram, and then it's far more usable. It's far easier to get your final mass from that. And because it's the mass of the product that we are calculating here, then that's why we would do product over reactant for that last but one calculation. Right, let's have a look at the next one. So have a go at this, pause the video and see how you can get on with this one. What is the mass of magnesium needed to produce 90 grams of magnesium oxide? Sorry, there's a typo there. It should be of magnesium oxide. Okay, we haven't suddenly switched over to Welsh. Okay, right, off you go, and let's see if you get the correct answer. Okay, so here we go. Okay, so this time it's the same equation, which is nice. Okay, so we kept that for you on purpose. Written that out again, make sure it is balanced, really important. Then the next step is to calculate the MR for both sides, so both magnesium and magnesium oxide. Again, ignoring the oxygen, it isn't needed in this calculation. Once again, we have the ratio of 48 to 80. Okay, so 48 grams of magnesium will produce 80 grams of magnesium oxide. Great. However, it's not very useful. We need it to 1 gram in order to make it easier to use. So for every 1 gram of magnesium, okay, what we're going to do this time is we're going to divide the reactants over the product, because we want to calculate the mass of the reactant this time. So 48 divided by 80 gives you 0.6, okay? And therefore 90 grams will produce 90 times 0.6, which is 54 grams of magnesium, okay? So this is an example of the other way around, if you like, where we're calculating the mass of the reactant this time. But all you do exactly the same procedure, exactly the same step by step, but on the last but one stage, you would be dividing reactant over product instead, okay? Because it's the mass of the reactant that we're trying to find out this time, okay? Okay, so have a look at that. In the next session, we will be a live session, which will also be stored on the Carlam Cymru website. We will go through another example of this kind of question for you in that, okay? But there are lots of examples that you can have a look at of this type of question, so really good to practice that. So we're coming towards the end of the session. We're going to look at empirical formula now. Okay, so first example, if there's a question such as, when 4 grams of copper oxide is reduced in a stream of hydrogen, 3.2 grams of copper remains. How much oxygen was contained in the copper oxide? So, typical question, this one, where you need to have masses of the elements involved, okay, in order to calculate a formula. This is the simplest formula, the empirical formula, okay? This question here gives you some of the information that you need. So it tells you that 4 grams of copper oxide is reduced, and 3.2 grams of that is copper. So the first thing you need to do is you need to calculate how much oxygen was present. And it's simple, it's really simple. 4 grams minus 3.2, and that gives you 0.8, which is how much oxygen was contained. Okay, so that's a nice simple calculation just to give you the mass of both elements within copper oxide. The next question, what is the empirical formula of copper oxide? Now, in order to do this kind of question, I would usually do it as a table form, okay? It doesn't have to be meticulous. It doesn't have to be done even with a ruler. Okay, just a very quick table format so that it minimizes the risk of making a mistake. Okay, so what we've got first on the top is the elements. So I've written down the elements present in copper oxide. That's really important. And they are, of course, copper and oxygen. The mass for both of those, which we calculated from the previous question, okay, copper was 3.2, that was given to you. Oxygen, 0.8, that is the amount that you actually had to calculate. Okay, so there you have 3.2 for copper, 0.8 for oxygen. The next thing you need to do is divide the mass by the AR for that element. So the AR for copper is 64 and the AR for oxygen is 16. So divide both of those. 3.2 over 64 gives you 0.05 and 0.8 over 16 gives you 0.05 as well. Now then, you have the same answer here in both of these cases. However, the next stage would be to divide with the smallest answer. Well, they're both the same. So you're just dividing by the same 0.05 in both instances, okay? And that will give you a ratio of 1 to 1. So if we look at the question again, what is the empirical formula, the simplest formula for copper oxide? Well, it is indeed CuO, okay, because there is one copper and one oxygen. That is the ratio of those elements. Okay, let's have a look at a different example. So find the formula of iron oxide produced when 44.8 grams of iron reacts with 19.2 grams of oxygen. Well, that's quite easy. They don't even have to make a calculation here. They are giving you the masses of iron and oxygen in that text there. So what I'm going to ask you to do now is pause this video, input the information into that table and see if you come out with the simplest formula for iron oxide. Right, let's have a look then. So we've put the masses in to begin with. So 44.8 grams for iron and 19.2 grams for oxygen. Then we divide with the AR. So for iron is 56 and oxygen is 16. So those divided gives you a ratio of 0.8 to 1.2. Now, the next step is to divide by the smallest number. Now we have 0.8 and 1.2. The smallest of those is obviously 0.8. So on the side with iron, we do 0.8 divided by 0.8, gives you 1. And for oxygen, you do 1.2 divided by 0.8, gives you 1.5. Now, we're almost there. The ratio is 1 to 1.5, but the problem here is a formula must have whole numbers. So we can't have, for example, FeO 1.5. That isn't correct, okay? We can't do that. So what we need to do, we need to get those two numbers, 1 and 1.5, well, the 1.5 at least, to a whole number. So what we can do in this instance is to multiply both of them by 2. So 1 times 2 gives you 2, and 1.5 times 2 gives you 3. So you have 2 whole numbers, okay, which gives you an empirical formula of Fe2O3. Okay, so that final step there, sometimes you will have to do that. Just ensure you have the smallest whole numbers in those ratios. And this is the final calculation we'll be looking at in this session. These are the RF values. Now, when you do chromatography, okay, you will have put some spots on a line on some special paper that you will put into a solvent. And what happens is you get a separation of pigments within that spot and a pattern, just like the diagram, for example, on the right-hand side here. Okay, now the RF value is gives you an indication of the solubility of a pigment within that spot. Okay, So the separated components of mixtures can be identified by calculating the RF value using the following equation. So here we have the RF value is the distance moved by the compound divided by the distance moved by the solvent. Okay. The RF value of a particular compound is always the same, but only if the chromatography has been carried out in the same way. Okay, you must be consistent. You must, for example, have used the same solvent, okay? Because that would vary. If you change the solvent, you will have different results. This allows industry to use chromatography to identify compounds in mixtures, okay? And this kind of technique is used in forensics, for example, okay? Might be looking at ink in pens, might be looking at components in blood, but it is a technique used by forensic scientists. To measure the RF of a substance, such as the red spot you can see on the right-hand side, you must measure the distance travelled by the red spot and the distance travelled by the solvent, then divide one over the other. So as you can see from the equation above, it's the distance moved by the compound, so the red spot in this case, over the distance moved by the solvent, which you can see in this diagram. Okay, so those two values that I've put in the diagram for you. Notice that the distance from the line to the red spot, what I've done is I've gone to the middle of the red spot with my arrow. Okay, that's really important. And that is a distance of 1 centimetre. Now, obviously, that's not to scale. Okay, but in an assessment, you may already have those figures given to you, such as 1 centimetre or 8 centimetres. If there are no numbers, then you will need to use a ruler and measure the distance of that spot yourself. Okay, so the red spot has travelled 1 centimetre, but the solvent has travelled 8 centimetres. So the RF value would be 1 divided by 8, and that gives you a value of 0.125. Okay, 0.125 is the RF value for the red spot. So let's have a look at the following then. So what I'd like you to do is calculate the RF values of the blue, yellow and green spots in this chromatogram. We have the distances written down for you, makes it nice and easy, okay, or a little bit easier at least. And you can see the distance travelled by the solvent. So pause the video, have a go at that. Can you calculate the RF values for those 3 spots? There is also a question at the bottom, which compound or spot is the most soluble in this particular solvent? And you can have a go at that as well. Okay, so let's have a look, see if you managed to do that. So our RF value of blue spot is 7 divided by 8 gives you 0.875. The RF value of yellow spot is 5 divided by 8 gives you 0.625. And the RF value of the green spot is 3 divided by 8, which is 0.375. Now, the compound which is most soluble in this particular solvent is the one that travels the furthest. Okay, so we can either look at the one that's traveled the furthest, which is the blue spot, or we can look at the RF values. Okay, and the most soluble have the RF value which is nearer to 1. Okay, so 0.875 is the nearest to 1 out of those 3 answers, and therefore that is the most soluble compound. Okay, all of the RF values will be between 0 and 1. So if you have a value that isn't between 0 and 1, then you've probably divided the wrong way. So just keep that in mind when you are doing this kind of calculation. Okay. So that is the end of this session, of session 4, on calculations in Year 10 Chemistry. Diolch yn fawr. Thank you very much for listening. We will be doing a live session, which will also be put on the Carlam Cymru website. So please have a look at that as well. If you can join us, fantastic. If not, it will be available for you to watch in the future. Thank you so much. Bye-bye.